IB Chemistry, Trends in Periodic Table. Now, if the stoichiometry part, what we did at the beginning of the year, is about the mathematical side of chemistry, and then later on we'll move down to energy and rates and equilibrium, that's more like maybe a little bit of physics in chemistry. Now this part, it's all about atomic bonding and models. It's a lot more like the English side of chemistry. So a lot is about giving concise answers with correct keywords. Okay, so as we are going through these topics, I want you to pay attention to the keywords, their definitions, and try to internalize it. Okay. Effective nuclear charge. Now, opposites attract. Therefore, the atom is held together by the attraction between the nucleus and electrons surrounding the core. The outer shell electrons, however, don't experience full attraction from the nucleus because of the repulsion from the inner shell electrons. As a result, the effective nuclear charge measures the attraction between the core and the valence electrons. So quantitatively, it equals to proton number take away the number of inner shell electrons. So basically, you're right, it basically equals to the number of outer shell electrons, or we can say that electrons at the highest principal energy level. So trends for effective nuclear charge. It increases across a period left to right, but remains similar approximately down a group. Now you'd ask why? Because across the period, the number of valence electrons actually increases, right? So across the period, we could imagine that effective nuclear charge will increase, but down a group, elements have the same number of valence electrons, and therefore its effective nuclear charge will remain similar. Trends in atomic radii. Atomic radius simply refers to how big an atom is. As the effective nuclear charge increases across the period, then electrons are more tightly held, literally. Okay. So we should expect that atomic size will decrease across a period, but it also increases down a group. Care to think about why? Now, moving down a group, we have additional electron shells added to each atom. So as a result, even though effective nuclear charge remains relatively same down a group, the atomic radii will increase. Here is an overview of atoms. As you can see that the top right-hand corner have some of the smallest atoms. Now, here's some concept that could be really confusing. If we are asking you about the trends for ionic radius, okay, so first of all, positive ions are smaller than their parent atoms, while negative ions are larger than their parent atoms. So you can imagine that when we talk about ionic radius, it's going to not exactly follow the trend of the atomic radius because negative ions are bigger and positive ions are actually smaller. Okay? So what we could imagine is, due to the loss and gain of electrons, the ionic radii decrease from group 1 to group 14 for the positive ions, but we can't really compare that straight away to the rest of the groups. We can only compare within group 1 to group 14, and then we can compare group 14 to group 17, and it still continues to decrease for the negative ions. The ionic radii will increase down a group as the number of electron energy level increases. First, ionization energy. Now, let's review the definition. Ionization energy refers to the energy required to remove 1 mole of electrons from a mole of atoms or ions in the gaseous phase. Remember, the keywords are gaseous, and it's always 1 mole. So we're basically talking about taking the energy required to take away the first electrons from atoms. So the trends in first ionization energy is that, first of all, noble gas have a full outer shell, a perfect 8. So they don't like their electrons pulled away. Then the further away from a perfect 8, it becomes easier and easier to take electrons from the atoms. As for group 1 metals, they want to be robbed of electrons anyways because they want to be that 1 plus ions, which also has a perfect 8. On the contrary, group 17 halogens wants to gain electrons to make a full outer shell, anions, which is also a perfect 8, but perfect 8 in the sense of it's an anion. So it's harder to take electrons from them. There we have it. Ionization energy increases across a period. This aligns with the increase of effective nuclear charge across a period. The nucleus has a larger hold on the outer shell electrons, and therefore it is harder to take them away. However, as we go down a group, atomic radii become larger or bigger. The core then has less and less effective hold on the outer shell electrons. So as a result, ionization energy decreases down a group. However, there are some kinks in the trend. So for example, between here, beryllium and boron, and magnesium and aluminium. So basically between group 12 and group 13. Now, this is because it is easier to take away the p electrons when the configuration is ns2 and p1 rather than breaking the complete ns2. You can also understand it as p orbitals have higher energy than s orbitals. So as a result, group 13 element has a lower ionization energy compared to group 12. Another kink appears here between nitrogen and oxygen, and also between phosphorus and sulfur. Now, here we have to show you the group 15 and group 16 electron diagram. As you can see that for group 16 elements, electron is taken away from a doubly occupied p orbital. That electron is much easier to get rid of because it is repelled by its partner, as opposed to group 15, which has a perfectly half-filled p orbital. It's harder to take electrons away from that group 15 elements. Now, electron affinity. The first electron affinity of an element is the energy change. So we're talking about enthalpy now. When 1 mole of electrons is added to 1 mole of gaseous atoms from 1 mole of gaseous ions to form 1 mole of gaseous ions. Now, so as the added electron is attracted to the positively charged nucleus, so the process is generally exothermic. However, the second and third electron affinity are defined similarly, but because the added electron is repelled by the negatively charged ion straight away, in this case, oxide ion, so that process will be endothermic because energy is needed for this process to occur. In summary, first electron affinity, usually exothermic, and second and third, usually endothermic. So from here, we can see from the data book that noble gases generally don't form anions, and therefore they don't have EA data. Most of the other elements, their first EA data will be negative. So trends for electron affinity. Electron affinities can be thought of as the negative of first ionization energy of the anion. Okay, so it decreases, or actually in value, in absolute value, it actually increases across the period. But because the value is negative, it's exothermic process. So we say EA decreases across the period as effective nuclear charge increases. We can think about group 17 elements as have the highest effective nuclear charge. Therefore, they attract electrons and form anions most effortlessly as compared to group 1 metals, which have lowest effective nuclear charge of approximately +1. The electron affinity reaches a maximum for group 2 and group 5 elements. Here. And these ones. Okay, so those are again kinks in the trend. That is really because group 2 elements have an electron configuration of ns2. So the added electron must be placed into a 2p orbital, which is really further from the nucleus. So those added electrons will experience reduced electrostatic attraction due to shielding from the electrons from the ns orbital. The value for beryllium is actually endothermic. As you can see, it's above the 0 mark, right? Because the electrostatic repulsion between the electrons of beryllium atom and the added electron is that big, so that to add a electron to beryllium, we have to give it energy rather than it releasing energy. So the electrons in the 1s and 2s orbital of beryllium is also shield the added electrons from getting some positive charge, positive attraction from the nucleus. Electronegativity. While electron affinity measures the energy released when forming anions, electronegativity also measures a similar thing. It's also a measure of the pull that the nucleus has on its surrounding electrons. But in this case, it measures the attraction of the electrons in a covalent bond. So an element with a high electronegativity has strong electron pulling power, and an element with a low electronegativity has weak pulling power to itself. And the reason that we say electron affinity versus electronegativity is really affinity measures the energy released when forming anions, and electronegativity is more of almost like a qualitative measure of the pulling power a atom has on a bonding pair. As you can imagine that the trend for electronegativity would somewhat align horizontally with effective nuclear charge, because the more the nucleus has a pull on its outer shell electrons, it's more likely to also pull a bonding electron towards itself. Okay, so horizontally, it increases across a period. Now down the group, it decreases really because, again, atoms are getting bigger and bigger, so the pull experienced by outer shell electrons becomes weaker. Something that's interesting to notice is that atoms with high first ionization energy usually have high electronegativity. So first ionization energy and electronegativity have the same trend. We can think about it in this way. So if a person is stingy, they don't want to lose money, they probably really want to gain money. Now, electrons to atoms are like money to people. Okay, so if an atom is stingy, they don't want to lose electrons, which means, okay, to take electrons away from them is going to require a lot of energy, so very high first ionization energy. In the same sense, if they don't want to lose money, they definitely want to gain money. As a result, the atom will have high electronegativity.